Good morning, students. In this video we will discuss the conjugate space H star. As we know, the conjugate space H star is collection of all the linear mappings from H to the field, say R or C, means all the linear functionals defined on H. So now in this section we will develop the features which are relative to operators, which we will discuss in the rest of the chapter. So let us say y be any vector in H. Then we consider a functional fy. We define fy on H to our field, whether it is R or C, by fy at x. This is just inner product of x and y. Because this y is in Hilbert space already, this is a fixed vector, and we define fy at any x in H. X and y both belong to H, and H is a Hilbert space, so this inner product is well defined, and this is a complex number. So here our field is just complex numbers because we are taking Hilbert spaces, so this inner product xy is complex number for all x in H. We define this function fy. Now we can easily see that this fy, this is a linear function, and this is continuous also, because we know the inner product is continuous. So if it is linear and continuous, so it is functional. If it is functional on H, then it belongs to H star. So for now, we can say for every vector y in Hilbert space H, if we define fy like this, that is a linear functional on H. And secondly, mod of fyx, this is mod of xy, and by Chevag's inequality we have this norm x into norm y. So from this we can say that norm of fy, this is less than equals to norm y, because we have proved norm of mod of fy at x is less than equals to norm y into norm x. So whenever we prove this thing in norm of tx for any linear operator t is less than equals to norm of t into norm of x, then we can say norm of t is less than equals, norm of tx is less than equals to k into norm x, then we can say norm of t is less than equals to k. So this norm fy is less than equals to norm y. Actually we want to prove that these two norms are equal. So let us say this equation is 1. Now if y is equal to 0, then this thing is obvious. Norm of fy, that is just norm y, because if y is 0, norm y is 0, and fy at any x, that will be just inner product of x and 0. So at any x it will be 0, so norm fy is 0. But in case y is non-zero, then norm fy, by definition, it is supremum of mod fyx at all the points x whose norm is 1. So since it is supremum, so it is greater than fy of the point y upon norm y. Because we know y is a vector in H and y upon norm y is a vector whose norm is 1. So this is one of the vectors x of this type. So supremum is greater than equals to mod of this quantity. And by definition, fy of x, this is just inner product of x and y. So when we calculate, this will be 1 upon norm y into inner product of y. So this is norm y, and we know inner product of y, this is just norm y square. So this is norm y. So here we have proved norm of fy is greater than equals to norm y. So let us say this equation 2. So from 1 and 2 we can say these two are equal. So from all these things we have proved here, we can conclude that if we define a mapping, let us say phi from h to h star, which maps y to the linear functional fy, then it is a norm-preserving map of h into h star. So we have this theorem. So we can firstly write a note. If we define a mapping phi from h to h star by phi of y is fy, where fy is the functional defined in the above manner, then phi is norm preserving map, because norm of y is equal to norm of fy. So this is norm preserving mapping of h into h star. Now we have a theorem which says that every functional, so from here we can say for every vector y we can find a unique functional fy which is defined in terms of inner product. But in the next theorem we will show that every functional in h star arises in this way. So theorem A of this section, that says if H is a Hilbert space and F be an arbitrary functional in H, H is a Hilbert space, F be any functional defined on H, or you can say F be any functional in H star, then there exists a unique vector y in H such that f of x is xy for each x in H. Or in other words, we can say there exists a unique y in H such that f is fy, because the functional fy is defined as fy at x is xy. So we can prove here for every functional there exists a vector y for which f is fy. So firstly we prove the existence of y and then we will prove uniqueness. So existence. Now if f is a zero functional, then obviously we can choose y is equal to 0. Because if f is 0 functional, then f of x is 0 for each x. And if we take y 0, then f of x is just inner product of x and 0, which ultimately becomes 0. So we can choose y is equal to 0. So let us assume f is non-zero. So if f is non-zero, let us take the null space of f is M. Let null space of f be M. Now we know that for a linear functional, the null space is proper closed linear subspace. So this M is proper. Why this is proper? Because f is non-zero. So there exist vectors where f is non-zero. So null space is a proper subspace. So M is proper and closed. It is linear subspace of H. And we know whenever we have a proper closed linear subspace, there exists a non-zero vector which is orthogonal to that linear space. So there exists a non-zero vector y naught in H such that y naught is orthogonal to M. So we will show that if alpha is a suitably chosen scalar, then the vector y is equal to alpha y naught. That is our required vector for this y naught. we show for a suitably chosen alpha y is equal to alpha y naught is our required vector. And now we have to prove that if this y is our required y, then for this y, f of x is equal to just the inner product of x, y. Now we will prove that for any scalar alpha, this thing is true for all vectors x in M. So for all x in M, what is f of x? This is because we are saying y naught is perpendicular to M. So let us start from here, x and y, which is x alpha y naught. So by properties of inner product, it is alpha bar x y naught. Now we know y naught is perpendicular to M. That means y naught is perpendicular to each of the vector of M. So for each x in M, this inner product is 0. So this will be 0. And since this is null space, M is null space, so for every x in M, fx is 0. So for each x in M, fx is 0 and xy is 0. Therefore, we can say fx is xy. But we have to prove this thing is true for each x in H, not for x in M only. But we have proved up to this that for every x in M, fx is 0. But because we have to prove this thing fx is equal to inner product of xy for each x in H. So in particular, it should be true for x is equal to y naught. So let us take f at y naught. If this thing is true for y naught, then fy naught, so we can write here, if fx is equal to xy for x is equal to y naught, then f of y naught will become y naught, alpha y naught, and this will be alpha bar norm y naught square. So we will choose alpha here to be, so from here we can choose alpha as conjugate of fy naught divided by norm of y naught square. So we will choose alpha as this value. So we have proved for every x in M, fx is equal to this for any value alpha. And we have chosen if this thing is true for x is equal to y naught, then our alpha is this. That means it is true for y naught also. Now because we know y naught is a vector which is perpendicular to M, and we know from a theorem that any Hilbert space H can be written as M plus M perp, which means direct sum of M and its perpendicular. Means and we know y naught is perpendicular to M, so y naught belongs to M perp. So any vector x in H can be written since any x in H can be written in the form M plus beta y naught, where this M is a vector in M and beta we will choose in such a way that this fx should be linear. So fx minus beta y naught, x minus beta y naught is equal to M. So f of M should be 0 because M is a null space. and because f is linear, so this becomes f of y naught, this is 0, and here beta is, because of this beta can be chosen fx upon f y naught. So we can now prove that 1 is true for every vector x in H. Let us see how. So for each x in H, fx, this is f of m plus beta y naught, and by linearity of f, this is fm plus beta fy naught, and this is my, because f of m is equal to my for each vector m in the space m, plus beta fy naught, that also we have proved that it is y naught y. So this becomes m plus beta y naught, and by linearity of inner product in the first component, and this is xy. So for each x in H, we have proved fx is equal to xy. So this completes the proof of existence. Now up to this we have proved for every functional f in H, we can find a vector y, which in this case is equal to alpha into y naught, which gives fx is equal to xy for all x in H. Now we prove the uniqueness. Now let us say there exists another vector y dash in H such that f of x is inner product of x and y dash for all x in H. Then from this we can conclude that xy is xy dash, and because of the linearity of inner product, we can say this is 0 for all x in H, because this thing is true for all x in H. Now if x in and y dash minus y, their inner product is 0 for all x in H, that means y dash minus y, this is orthogonal to the Hilbert space H, because this is orthogonal to each of the x, and we know 0 is the only vector which is orthogonal to every vector. So y dash minus y is 0, which means y dash and y, they are same. So this completes the proof of uniqueness. So from this theorem, before this theorem we have proved that for every vector y we can find a functional fy. So for every y in H there exists fy in H star. But in this theorem we have proved that for every functional f in H star there exists a unique vector y for which f is equal to fy. Which means the phi mapping which we have defined earlier from H to H star, that is actually a surjective mapping, by because in this theorem we have proved for every vector for every functional here there exists a unique vector here whose image is this. So it means this phi is actually an onto mapping also. So we can say, combining these results, we can say phi is non-preserving map of H onto H star. And secondly, we can also prove that this phi is a linear mapping, which means phi of y1 plus y2, that is phi of y1 plus phi 2. That means f y1 plus y2, this is f y1 plus f y2. And that we can easily prove because f y1 plus y2 at any x in H, that can be inner product of these two, and by linearity of inner product, we can write like this. So it is fy1 of x, fy2 of x. So from here we can say fy1 plus y2. This is fy1 plus fy2. Similarly, we can prove that phi of alpha y, this is alpha bar of phi y. Now in this case, we can say phi of alpha y is alpha bar. So this is actually not a linear mapping, but this is near to linearity. So we cannot prove this is linear, but if it were linear mapping, then it will be an isometry, because it is norm preserving also. We have proved norm of y is equal to norm of fy. So if it were linear mapping, then it will be an isometry.